I'm just going to do a couple more examples of finding the concavity for a function using the second derivative. We have another polynomial here, f of x equals x to the fourth minus 6x cubed. So let's do the same thing we did at the end of the last video. Let's find the second derivative, which means first we've got to find the first derivative. So first derivative is 4x cubed minus, see, 6 times 3, when we bring down the 3, gives me 18x squared. And then find the second derivative. So we'll take the derivative again. Let's see, 4 times 3, when we bring the 3 down, I get 12x squared. And when I bring the 2 down, 18 times 2 is going to give me 36x. And to make our sign chart, we need to set this second derivative equal to 0. So let's set this equal to 0. Both of those coefficients are divisible by 12, and both terms have an x. So I'm going to factor out the 12 and the x. That leaves me with an x and a minus 3. So we're solving a quadratic equation. We're going to set both factors equal to 0. So I've got 12x equals 0 and x minus 3 equals 0. And divide by 12, I get x equals 0. And I've got plus 3. I've got x equals 3. Okay, so I have two potential inflection points where the concavity might change. So let's set up our interval. And I'm going to put x equals 0 and x equals 3 on my number line. All right, so we're going to put information about the second derivative above the number line, information about the original function below the number line. Let's see, let's pick any number to the left of 0. Anything negative will do. I'm going to pick -1. So we're going to find f double prime of -1. In between 0 and 3, 1 sounds like a good choice. And past 3, any number will do. Pick the smallest thing I can. We're going to find f double prime of 4. All right, so we got a lot of work to do. We're going to plug into this second derivative here. So I've got f double prime of -1, f double prime of 1, and f double prime of 4. So all three of those are getting plugged into our second derivative. Let's see what happens. All right, had to pull out the calculator there for the last one. All right, so we got something positive in this region. We got something negative in this region and something positive over here on the right. So again, because this is the second derivative, these things are going to tell us about concavity. So any place where the second derivative is positive, we're going to be concave up like a cup. So that's going to be in this region. And then in the middle where we had negative second derivative, we're going to be concave down like a frown. All right, so we'll say our intervals of concavity. We're going to say that f of x is concave up on two intervals, so -∞ to 0, and then from 3 to infinity. Okay, using that u to say that both of those intervals are part of my concave up answer, and then f of x is concave down on the interval in between, so from 0 to 3. All right, so since we had concavity changing at both of those places on that number line, we're going to say that both of these points are going to be inflection points. Okay, so we're going to say that f of x has inflection points at x equals 0 and at x equals 3. All right, let's do one more example of finding concavity for a function. We've got the cube root of x minus 1, and we're going to find the second derivative. So let's rewrite this. We know as x minus 1 to the 1/3 and find some derivatives. So f prime of x, we're going to bring down that 1/3 exponent. We're going to subtract 1 from the exponent. 1/3 minus 1 is equal to -2/3. And this is a chain rule. We're going to leave the inside function alone times the derivative of the inside function, which in this case just happens to be 1. All right, that's our first derivative. Now we're going to use the chain rule again to find the second derivative. The 1/3 is going to go along for the ride. And we're going to bring down the -2/3. So we're going to have times -2/3, leave the inside function alone. we're going to subtract another 1 from negative 2/3. So again, if you need to, always come do your scratch work. Negative 2/3 minus 3/3 gives us negative 5/3. All right, so our exponent is negative 5/3. That was the derivative of the outside function. Leave the inside function alone. And again, multiply by 1. And I know I'm going to be trying to figure out points where this is equal to 0 or undefined, and we're going to try to plug stuff into it. So let's rewrite this in a little bit easier to read way. So I'm going to bring that negative 5/3 exponent down into the denominator. So I'm going to have an x minus 1 to the 5/3. And let's see, I've got a 3 and a 3 down in the denominator. Those are going to be equal to a 9. And then I'm going to have a negative 2 left up top. So that's my second derivative. So as usual, we're looking for places where this is equal to 0 or where it's undefined. It's never going to be equal to 0. Remember, that would be where the numerator would equal 0. Negative 2 is never equal to 0, but the denominator might be equal to 0. So let's set 9 times x minus 1. 9 times x minus 1 to the 5/3 equal to 0. Divide both sides by 9. And we'll get x minus 1 to the 5/3 equals 0. And then we've done this in a previous video where we raise both sides to the reciprocal power. So we're going to raise both sides to the 3/5. That will cancel out that exponent. We're multiplying exponents. So we get x minus 1 equals 0. Add 1 to both sides and you get x equals 1. All right, so that's the number that I need to put on my number line. I think I need a little more room, so we'll go to a clean slide. All right, there's our original function and our second derivative. We just got done finding out that this derivative might change sign at x equals 1. So that's what's going to go on my number line, x equals 1. And we're going to say things about f double prime on top. We're going to pick points that are on either side of 1. So to the left of 1, I'm going to pick f double prime of 0. And then on the right, I'm going to pick f double prime of 2. And we're going to plug those into the second derivative. All right, so I'm about to plug into the second derivative, things down in the denominator to the 5/3 power. I'm going to rewrite that fractional exponent in root notation so that it'll be easier for me to evaluate. So I've got negative 2 over 9. This is actually the cube root of x minus 1 to the 5th. All right, so let's plug in f double prime of 0 and f double prime of 2. So f double prime of 0 will be negative 2 over 9 times the cube root, 0 minus 1 to the 5th. All right, I'm really just keeping track of whether things are positive or negative. So 0 minus 1 is negative 1. Negative 1 to the 5th is negative 1. The cube root of negative 1 is negative 1. So this whole thing is negative 2 over 9 times negative 1. Negative over negative is going to give us a positive number. And I really don't even care that it's 2/9. I only care that that is a positive number. Then I'll find f double prime of 2. Okay, we've got a negative 2 on top, a 9 cube root, 2 minus 1 to the 5th. Again, just kind of some mental arithmetic because it's pretty easy. 2 minus 1 is 1. 1 to the 5th is 1. Cube root of 1 is 1. So again, we've got a 1 down there, but this time it's a positive 1. So 2 over 9 times 1. I get a negative number this time. So there's a negative answer for f double prime of 2. So again, we're going to make statements about the original function. So f of x down here in green. Let's see where the second derivative is positive will be concave up. Where the second derivative is negative will be concave down. And then we'll make our statements. All right, so we'll say, see, I don't have a lot of room. F of x is concave up on negative infinity to 1 and concave down on 1 to infinity. And again, we ended up changing concavity at our point on the number line. So we're going to say at x equals 1, we've got an inflection point. All right, so we'll do much more with these kinds of intervals when we get together on Zoom.